Hello everyone. Today I am going to explain about the calculation of rectifier efficiency and the transformer utilization factor and percentage regulation of a rectifier. First I am going to explain about the rectifier efficiency. So what is the rectifier efficiency here is the rectifier efficiency tells us that what percentage of total input power, that is total AC input power, is converted into useful DC power. Actually what is the rectification means here is the rectifier will convert AC to pulsating DC. So pulsating DC means here it consists of some part of AC and DC value at the output. So here from the total input power, how much it will be converted into the DC. So that's what it will indicate. The efficiency will indicate here. Rectifier efficiency tells us that what percentage of AC input power is converted into the useful DC power. So that is given by our rectifier efficiency. Okay. So then here what is the definition of that rectifier efficiency? Formula wise here is rectifier efficiency neta is equal to DC power delivered at the output by AC input power from the transformer secondary. So why I have mentioned here is, here if you consider this is the transformer. So here we have the step down transformer for our rectifier. So this one is nothing but the secondary voltage what we are going to apply for the diode. That's why we have to consider the AC input power as the secondary transformer secondary input voltage and input power. Okay, so that is the point you have to remember here. That's why I have taken that the formula for that is it is the ratio of DC power delivered to the AC input power from the transformer secondary. So here we have to consider that percentage. How much percentage? That's why I have multiplied with the 100. Okay, so this is the formula for rectifier efficiency, generalized formula. So here neta is equal to DC power delivered, I am taking as P suffix DC. Here DC and P indicates the power and DC indicates the DC power delivered by PAC, multiply with 100. So what is PDC generally? What is power means here? We have power in terms of current and resistance as like this, and at the same time V into I. So product of voltage and multiply with current, you will get the power, and similarly you can also have I square into RL. Okay, so this is also the equation in terms of the current and the load resistance. So the same formula I am going to use here. I want the DC power. So I require the DC power, therefore PDC is equal to IDC square into RL. So this is nothing but IDC square into RL. Instead of I am substituting IDC square, and RL is the load resistance. So now what happened here? Here IDC is equal to, in the previous discussion we have calculated IDC is equal to Im by pi. So I am substituting this IDC value in this equation so that I will get PDC is equal to Im by pi whole square into RL. Now I am considering this equation as equation number 1. Now AC, what is AC input power? In the previous discussion we have calculated that AC input power is equal to IRMS square multiply with RF plus RL. So here IRMS square multiply with RF plus RL. So here we know that IRMS is equal to Im by 2. So if you substitute IRMS value in this one, that is nothing but Im by 2 whole square multiply with RF plus RL. So therefore the input AC power is equal to Im by 2 whole square RL plus RF. So therefore neta is equal to PDC by PAC multiply with 100. So what is PDC from equation 1? That is Im by pi whole square into RL, and here we got PAC as Im by 2 whole square into RF plus RL, here multiply with 100. So if you rearrange the terms, that is by taking the square, neta is equal to, that is efficiency is equal to Im square by pi square and this one becomes 4 square, that is 2 square is 4 by Im square. So this Im square will cancel with this one, and the remaining is what we have is it is 4 by pi square. It is neta is equal to, or efficiency is equal to, efficiency is equal to 4 by pi square RL by RL plus RF into 100. So here 4 by pi square, if you calculate by using the calc here, you will get 40.52 will get, and here I am taking this multiplication 100, I am considering as percentage. So it is 40.52 RL by RL plus RF. So this 40.52 I am making that one as, that is round figure, that is 40.6. Okay, by I am taking this one R, I am multiplying and dividing with I am taking this RL common, so that RL and RL will cancel. So if I take here, if it is RL, so RL will cancel with this one. So the remaining equation for us is, that is 40.6 by 1 plus RF by RL. So that is the point we have to remember here. So here efficiency is equal to 40.6 by 1 plus RF by RL percentage. So but if you consider that if RF, that is forward resistance, is generally very less and it is less than RL, therefore we can neglect this RF value. Okay, so what happened here, if I neglect this one, it is 0, its ratio is 0 because RL is very greater value, so we will get neta is equal to 40.6%. So what it indicates here, okay, out of the total 100% AC power, it will convert only the 40.6% of DC power, and the 60% almost it is wasting. Okay, so that's why here we have neta is equal to 40.6%. Okay, so what it will indicate, so this percentage it will indicates means only 40.6% is of AC is converted into the DC, and the remaining power is wasted. Okay, so that's what here the efficiency will gives for an half-wave rectifier. Okay, so this rectifier efficiency is calculated. Now we are moving to the transformer utilization factor. So what is transformer utilization factor means, here we are taking the input from the transformer secondary. Okay, so how much value or how much AC power we are using or we are utilizing, that will be indicated by this transformer utilization factor. So what is the definition of transformer utilization factor? So it is the ratio of DC power delivered to the load to the AC rating of the transformer secondary. Okay, here we have the difference between the AC input power and the AC rating of the transformer secondary. Okay, so that is what we have to remember here. It is the ratio of DC power delivered to the load to the AC rating of the transformer secondary. Okay, so what is AC rating means here? We will see. So here transformer utilization factor is equal to DC power delivered to the load is PDC, and AC rating of the transformer secondary I am taking as PAC rating. Okay, so here we know that PDC is equal to IDC square into RL. So IDC we know that Im by pi. Okay, so therefore I am substituting in place of IDC Im by pi, so it becomes Im by pi whole square multiply with RL. Okay, so this equation I am taking it as equation number 1. Now I want to calculate here the AC rating. Okay, PAC rating or the secondary transformer rating. Okay, so here AC rating of transformer secondary or the AC power rating is PAC rating I am indicating. So here we have to calculate, generally power is nothing but voltage multiplied with the current. So here we to calculate the AC rating of the transformer secondary, so we have to consider VRMS value, IRMS value. The effective voltage of the RMS value, that is nothing but effective voltage, effective input voltage, and multiply with the effective current or we can also consider that the RMS value of the transformer secondary voltage multiplied with the current that is flowing, that is IRMS. So here we will get the transformer secondary rating. Here we will get the transformer secondary rating by multiplying with the RMS value of voltage and the current. Okay, but here we know that IRMS value we have calculated in the previous discussion, that but we don't know the VRMS value of the secondary voltage. Okay, secondary rating. So that's why here I will calculate VRMS. So it is square root of 1 by 2 pi 0 to 2 pi Vi square d omega. So here why I am taking the limit 0 to pi. Okay, there while calculating VRMS value, normal VRMS value, so we will consider from 0 to pi because we are getting the output at that point. But here it is not the case. We have to calculate the RMS value of the secondary winding voltage. That's why here that will give us the at the input side or the Vi. So we will have the complete cycle, not half cycle we have to consider. So complete cycle means you have to consider complete time period, that is 0 to pi. So therefore it is square root of 1 by 2 pi 0 to 2 pi Vi square d omega t. So it is, now I will substitute Vi is equal to Vm sin omega t. Vm sin omega t, the input voltage for 0 to 2 pi. Okay, so that's why here we are going to calculate the VRMS as for 0 to 2 pi. So it is root mean square value of voltage, that is at the transformer secondary winding or the input voltage. So I am substituting in place of this value. So it becomes square root of 1 by 2 pi 0 to 2 pi Vm sin omega t whole square d omega t. Okay, so here we will get this one as Vm square sin square omega t. So therefore it is square root of 1 by 2 pi, it is 0 to integral 0 to 2 pi Vm square sin square omega t d omega t. Okay, but we know that the sin square omega t we can write it as 1 minus cos 2 omega t by 2. So the same thing I have written here, that is Vm square by 2 pi and it is 0 to 2 pi, and in place of this I am writing as 1 minus cos 2 omega t by 2 multiply with d omega t. Okay, so now what happened here, I am taking this integration into the bracket, therefore it is square root of Vm square by 4 pi and it is 0 to 2 pi 1 here, that is 1 d omega t, and it is 0 to 2 pi cos 2 omega t d omega t. So now what is the integration of 1 here, that is nothing but the variable, that is d omega t, and it's here it is d omega t. Okay, so d omega t means here you will get is omega t to the limit 0 to 2 pi. So if I substitute these limits here, it becomes Vm square by 4 pi square root of multiply 2 pi minus 0, you will get 2 pi, but if you substitute these two limits here, it is sin 2 omega t, that becomes what, omega t is equal to 2 pi, therefore it becomes sin 4 pi minus sin 0 by 2. So what is the sign of pi? Either it may be sin pi, sin 2 pi, sin 3 pi, like that we will get the 0 value. Okay, so that's why this total term will becomes 0, and the remaining term is what we have. This will cancel with 2 pi, with 4 pi by 2 times. Therefore it will become square root of Vm square by 2. Okay, so what is the square root here? Vm square is nothing but Vm, and for 2 it is square root 2. So therefore VRMS is equal to Vm by root 2. So now what is our equation here? Transformer utilization factor is equal to PDC by PAC rating. Okay, so therefore here PDC is already we have calculated, that is Im by pi whole square into RL. So this is the one. Next, what is PAC rating here? VRMS into IRMS. So we know that VRMS is equal to, now only we have calculated, that is Vm by root 2, and we have here IRMS I have calculated in the previous discussion, and you have that IRMS is equal to Im by 2. So if you substitute all these values, that is this one and VRMS value and IRMS value, So we'll get what? Im square by pi square and multiply with RL by Vm by root 2 multiply with Im by 2. Okay, so this is about up to this point, that is TUF. Okay, so now TUF is equal to, what we have here is Im square by pi square and it is multiplied with RL, and here we have it is Vm multiplied with Im and it is 2 root 2 by Vm multiplied with Im. Okay, but what is Vm here? Vm is equal to Im multiplied with RL plus RF plus RS. Okay, so if we substitute this value in this one, therefore we will get TUF is equal to Im square by pi square multiply with 2 root 2 by, what is Vm value here? Im RL plus RF plus RS. So therefore here Im RL plus RS plus RF. It is multiplied with Im here and we have RL. Okay, so therefore here Im square will cancel with Im and Im, and we have here 2 root 2 by pi square multiply with RL by RL plus RS plus RF. So we know that RL is the load resistance, RS is the transformer secondary winding resistance, and RF is nothing but the forward bias resistance. Okay, so this is about the TUF we got here. Then what is the value of this 2 root 2 by pi square? So this is TUF value if RL is very greater than RF plus RS. So what we will get here? Therefore TUF is equal to 2 root 2 by pi square multiply with RL by RL. So these two will be cancelled and we will get here it is 2 root 2 by pi square. The actual equation is this one. If we consider the condition that if RL is very greater than RF plus RS, so we can neglect this RF plus RS, so it becomes what? RL and RL. So it will be cancelled and the remaining one is 2 root 2 by pi square. So what is its value here is TUF is equal to 0.287. So this is the transformer utilization factor of our off-wave rectifier. Okay. Now we will calculate the percentage regulation. So here what is percentage regulation means? Here we have the definition. The variation of DC output voltage as a function of DC load current is called as percentage regulation. So the variation of DC output voltage as a function of DC load current is called as percentage regulation. Then what is the formula to calculate this percentage regulation is, it is nothing but VDC no load minus VDC full load by VDC full load. So what is full load and what is no load? So no load means if you cannot connect any load resistor, then what is the VDC value? So we have here, and at the same time VDC full load means if you consider all the three resistances, that is load resistance and forward bias resistance and secondary winding resistance, all the three if you consider and if you calculate, that is nothing but VDC full load. Therefore percentage regulation is equal to VDC no load minus VDC full load by VDC full load. Okay, so this equation I am taking as 1 because here we are multiplying with 100 because we have to calculate percentage regulation. So here VDC no load, that is equal to Vm by pi. So this equation is cannot depends on any load resistance, that's why it is considered as the VDC no load, that is Vm by pi. Then what about the VDC full load? VDC full load is equal to IDC into RL. Okay, load I am taking here full load. If you apply the load then what is the VDC value? That is the current IDC multiplied with the RL, so that we will get IDC into RL is the VDC full load. Then what is IDC here? We know that IDC is equal to Im by pi. So therefore Im by pi into RL. Okay, so this VDC full load is equal to IDC into RL, and that is equal to Im by pi into RL. So here IDC is what? Im by pi. So we are substituting that one. Next, but we know that Im is equal to Vm by RL plus Rf plus Rs. Okay, the total current, maximum current or peak current is equal to Vm by RL plus Rf plus Rs. Okay, so therefore substitute this one in this equation so that you will get VDC full load. VDC full load is equal to Im. Im is equal to Vm by RL plus Rf plus Rs. So I am substituting that one as Vm by, already we have the pi, therefore pi into RL plus Rf plus Rs, and it is multiplied with RL. So this equation I am taking as equation number 2. So now, this equation I am taking as equation number 3. So here from this equation number 2 and equation number 3, substitute the VDC no load and VDC full load in the equation number 1. So what you will get here, VDC no load is nothing but Vm by pi, and VDC full load is nothing but Vm by pi RL by RL plus Rs plus Rf. Okay, and it is divided with the VDC full load, that is Vm RL by pi into RL plus Rs plus Rf into 100, because it is percentage you have to calculate. Therefore percentage regulation is, here the common term is Vm by pi and Vm by pi. So I will take the common Vm by pi, so that we will get 1 minus RL by pi into RL plus Rs plus Rf divided by Vm by pi RL by RL plus Rs plus Rf. Okay, so if you consider here this one, this Vm and this Vm will cancel, because Vm by pi is there in the numerator and denominator Vm by pi, so these two will be cancelled, and what we have here is 1 minus RL by RL plus Rs plus Rf, and it is RL by RL plus Rs plus Rf. So if you consider here the LCM here, it becomes RL plus Rs plus Rf minus RL, so RL and RL will cancel, and we have here, that is this value is also cancelled. Okay, RL plus Rs plus Rf, and with RL plus Rs plus Rf. So what we have remaining is Rs plus Rf, that is equal by RL is into 100. Because why I am considering this will goes to the numerator, so that it will be cancelled, and it becomes RL will become some multiplication for RL plus Rs plus Rf in the denominator. So therefore this term and this term will cancel, and RL will cancel, and the remaining terms are Rs plus Rf multiply with RL. So therefore it is Rs plus Rf multiply with RL by 100. So this is the value or the equation of percentage regulation. Okay, so if here we consider another assumption, if Rf is very greater than Rs, that is secondary winding resistance. So if you neglect that Rs, so what we'll have here, only Rf will be there. So therefore percentage regulation is equal to Rf plus RL into 100. Okay, so this is the percentage regulation if you neglect Rs value. Otherwise we'll have the complete equation Rs plus Rf by RL into 100, that is percentage regulation. Okay, so this is about the calculation of efficiency, transformer utilization factor, and the percentage regulation of a rectifier. Okay, thank you for watching. Subscribe our channel.